This lecture is going to introduce vapor power cycles. In particular, the cycle that we're going to look at is known as the Rankine cycle. So we'll begin by looking at the basic Rankine cycle that only consists of 4 components. Now, although that would work, all Rankine cycles that are implemented in practice have certain additions or certain enhancements to the basic cycle that make them much more efficient. So two of those that we're going to look at is the concept of reheat, and secondly the concept of regeneration. And regeneration, we'll see, is achieved by 2 different components, an open feedwater heater or a closed feedwater heater. So we're going to look at a Rankine cycle with reheat and with regeneration achieved through an open and or a closed feedwater heater. So the layout of the plant is going to be quite a bit more complicated than it was for refrigeration systems. There we had the same 4 basic components in every system. Here there's going to be quite a bit more variability. Well, we're going to begin the Rankine cycle the same way as we began refrigeration. We're going to start with a Carnot cycle. Now, a Rankine cycle is a heat engine or a power cycle, so we're back to looking at the Carnot cycle in the way that we very first introduced it, and that is as a power cycle. Now, similar to refrigeration systems though, we're going to be operating with a working fluid, water in this case, which is changing phase. So we're going to be in or near the liquid vapor region. So if we look at our TS diagram here, this is the same starting point as for refrigeration systems, only now we're going around this in a clockwise direction, which is the same way that we originally introduced the Carnot cycle. So we have here our reversible adiabatic compression, constant temperature heat addition, a reversible adiabatic expansion, and finally constant temperature heat rejection. So those same 4 basic Rankine cycle processes. And in addition, for a Rankine cycle, all 4 of these processes are reversible. So 2 constant temperature, 2 isentropic. So it's a rectangle on a TS diagram. Now here's a little schematic of a plant layout that might achieve that. So we have first of all a compressor taking us from 1 to 2, and that would be a reversible adiabatic compressor. We have a boiler taking us from 2 to 3, so converting the saturated liquid to saturated vapor. Then we have a turbine from 3 to 4, so this is a reversible adiabatic turbine, so vertical line. And then finally we have a condenser taking us from 4 to 1. So going from a mixture with lots of vapor and very little liquid to a mixture with a lot of liquid and very little vapor. So heat is added to the cycle in the boiler, removed from the cycle in the condenser, work is produced by the turbine, and work is consumed by the compressor. So compressor, boiler, turbine, and condenser. Now, just like for the refrigeration system, there were problems operating completely inside the liquid vapor region. This current Carnot cycle has the same problems. The first one of those that we're going to talk about is that we really can't compress effectively in the liquid vapor region. So we can't compress a liquid vapor mixture efficiently. So if we go back to our TS diagram, it's this process that we're talking about, the compressor. So going from a liquid vapor mixture and compressing it up to a saturated liquid, very difficult to do that efficiently. So that's the problem. Now the solution is actually very similar to what we did in the refrigeration system. There we took care of that problem by moving the compression out into the vapor region. Here we're going to do exactly the opposite. We're going to take care of that problem by moving that compression into the liquid region. So we're going to completely condense in the condenser before we go and try to do the compression. And then, because we're compressing a liquid, it won't be a compressor, but it'll just be a liquid pump. So that's the first change we make, and that actually gets us to a basic Rankine cycle. So this is no longer a Carnot cycle, it is now a Rankine cycle. In terms of the 4 components, we still have a turbine and a condenser. The boiler, I've just generalized the name a little bit. It's typically called a steam generator in a Rankine cycle, but still the same basic function. adding heat to the cycle. The biggest difference is the compressor is gone and we now just have a pump here. So we'll come out of the condenser as a liquid into the pump and pressurized from the condenser pressure to the steam generator pressure in a pump instead of in a compressor. Now we want to see what this looks like on a TS diagram. So this is the same TS diagram as before, just with a liquid pump instead of with a compressor. Now a couple of things about this TS diagram. First of all, it is drawn to scale. The saturated liquid and saturated vapor lines here are plotted using real data from your textbook, and we see now that instead of having a compression process completely inside the liquid vapor region, the condenser has now condensed all of the liquid, so we have 100% liquid, saturated liquid line, and then we compress. So we go straight up, so this is an isentropic pump, straight up to the steam generator pressure. So the steam generator line of constant pressure we'll see is like this out in the vapor region, then cuts across and then goes down like this. Currently this plot is enhancing the difference between this line of constant pressure and the saturated liquid line. We're going to look at this in detail later on, but if this were actually drawn accurately, this line would be very, very close to the saturated liquid line. I've just enhanced that difference a little bit so we can see the compression process from 3 to 4 a little more clearly. So that's the big change from a Carnot cycle to a Rankine cycle, is the compression process moved into the liquid region and achieved with a pump. So notice this is no longer a Carnot cycle because our heat addition process now, which happens from 4 to 1, so 4 being the inlet of the steam generator, 1 being the exit, it's no longer happening at constant temperature. The temperature increases during this part of the steam generator, and then finally it's constant for the last portion of it. So it's not a Carnot cycle anymore because the heat addition is no longer at constant temperature. Now there's still a problem with this. We've been talking about this side of the cycle, which happens over here, but there are also similar problems over with the turbine. Currently, we're asking this turbine to accept a saturated vapor and produce work isentropically, and its exit is a mixture of liquid and vapor. Well, that also is difficult to do. We want to, as much as possible, have these turbines working out in superheated vapor region. It's not always possible to eliminate completely the liquid that shows up in the turbine, but we certainly want to try to do a better job than this. So we want to move this turbine process out into superheated vapor region. So that's the next problem. There's too much liquid in the turbine, and our solution, first solution, is to add a superheater. Turns out there's a couple different ways to address this problem, but the first one is we're going to superheat the vapor going into our turbine. So in terms of the components, there's no difference here. The superheater is just combined into the steam generator, so this is just going to have a higher exit temperature than it used to. So we're adding additional heat in the steam generator. And the effect on the TS diagram is to move this turbine process from 1 to 2 from here, where it used to be, out mostly into the superheated vapor region. So this is still a line of constant pressure. So all the way from 4 up here, across and up, that's a line of constant pressure at the steam generator pressure. So the exit of the steam generator, entrance to the turbine, is at this point here. So because we've added more heat, we've moved the turbine process to the right. Therefore, this portion of the turbine is dry, meaning there's only vapor in it. It's only at this bottom portion where we start to get a little bit of liquid showing up in the turbine. So that is a much more realistic cycle. So now we've got a Rankine cycle where the turbine process is much more realistic. Now we would still like to move this turbine further to the right. Now the next problem we want to address is related to the fact that this line is really quite steep. Now the reason that that's important is to move this turbine process over to the right far enough to get this bottom region of the turbine out into the superheated vapor region, the temperature at point 1 is going to get very high, and that's because this line is very steep. Remember, this is drawn to scale here using real data, so we can see this line is just getting steeper and steeper. So to try and move that over further to the right, temperature there is going to get extremely high. So the problem with this configuration is that we can't superheat high enough because the temperature at the turbine inlet will get too high. So the combination of pressure and temperature at that point will just be too high for the materials to handle. So the solution to this is to add one or more reheaters. So this brings us to the idea of reheat in a Rankine cycle. So how does a reheater work? Well, we see the change here when we add a reheater to our plant layout. The condenser, the pump, steam generator, that's all the same. But instead of a single turbine, we now have two turbines. So this is called stage 1, and that's stage 2 of the turbine. And what we do is between the two stages, we add a reheater. And a reheater is just another name for a heat exchanger. So we're certainly supplying heat to this thing in the steam generator from some external source. Well, we're also supplying heat in the reheater. So we take the steam out of turbine 1, add more heat to it, which is called reheat, and then back into the second turbine stage. And what this looks like on a TS diagram is we now see two turbine stages. So turbine 1 goes from point 1 down to point 2. Then we add reheat, so this is a constant pressure heat addition process from 2 to 3, so that's taking us through the reheater, and just like every heat exchanger, that's a constant temperature process. So we're going from 2 to 3, and then finally 3 to 4, we're going down through a second turbine. So this is a reversible adiabatic expansion. So we've managed to move this second turbine process far enough over to the right that there's only a little bit of liquid showing up in the very last parts of the turbine. So this is probably a successful implementation, and these turbine stages would be able to run for many years without degrading. Now it's possible under some conditions that we might even have two reheaters. So this shows the plant layout with two reheaters, so we now have 3 turbine stages because we have 2 reheaters, and so we add heat at both of these reheaters. So the TS diagram as a result has 3 turbine stages: stage 1, stage 2, and stage 3, and 2 reheaters. 2 to 3 is our first reheater, and 4 to 5 is our second reheater. And depending on the conditions we're running at, it might be necessary to have those 2 reheaters to move this last turbine stage over far enough that we avoid significant liquid showing up in the latter stages of the turbine. So this Rankine cycle is now able to avoid the problem of significant liquid showing up in the turbine by using reheat. Now the problem with this is that we would still like to achieve a higher efficiency than is possible with our current configuration. So we want the highest possible thermal efficiency that we can get. So let's just remind ourselves what thermal efficiency is. It's the net work divided by the heat supplied. So notice we're adding heat to this system in the steam generator, and if we have reheaters in operation, we're also adding heat in those reheaters. And the net work is going to be the work that the turbines produce plus the work that is required by the pump, which of course will be negative. So the net work divided by the heat supplied. Well, this brings us to the concept of regeneration. So our solution to this is going to be to add regeneration to this cycle, and there's 2 different ways that we can achieve that, either with an open or a closed feed water heater. So we're going to talk about both of these new components next. Now, first of all, regeneration in general is a process where we steal a little bit of energy from one point in the cycle and use that to reduce Q dot H. So in other words, to reduce the amount of energy that we need to supply to this cycle from outside. So if we can reduce this, we will increase our thermal efficiency. So that's what feed water heaters do. They reduce the amount of energy that we need to supply from outside the cycle. So regeneration in general then is using energy from a hot part of the cycle to reduce the external heat input. That's an important part of this. The external heat input required at low temperatures. So first of all, we need to define a new term here that has popped up, but we haven't really defined it yet. Here's our basic Rankine cycle, so the condenser, the pump, steam generator, and the turbine. This is the feed water. So the water being fed from the pump into the steam generator is known as the feed water. And it's important to define that here because we're going to look at two different styles of feed water heaters. So the idea behind regeneration is to preheat this water before it gets to the steam generator so that we don't have to supply so much energy in the steam generator from an external source in order to feed the turbine. So we're heating this feed water with a feed water heater. So there's two different versions of this, an open feed water heater and a closed feed water heater, and we're going to look at open first and then closed, and we'll see where they get those names when we look at the details of how they work. So first of all, an open feed water heater. Well, I haven't added the open feed water heater yet. The only thing I've done here to the basic Rankine cycle is I've split the turbine into two stages. Notice I don't have a reheater in here. I don't want to look at reheat and regeneration at the same time. We'll see that when we bring this all together at the end. So we're going back to our basic four components. The only difference is I've split the turbine into two stages. And the reason I've done that is I want to extract a bit of steam from between these two turbines. And I just show them as split into two stages so I can show that clearly. So the open feed water heater goes on the feed water line. So between the pump and the steam generator, we add our open feed water heater. And this is called an open feed water heater because it's just an open chamber. In fact, it could be as simple as just a T in the line. Because what we do is we take steam that we've extracted from between these two turbines and we feed it into this open feed water heater. So this schematic shows the final configuration for a single open feed water heater added to a basic Rankine cycle. So we have our feed water coming out of the pump, entering the feed water heater. So this is a relatively large flow rate of relatively cool water. Then we take a relatively small flow rate of extracted steam, so this will be at high pressure and temperature, and we mix these together. So these just enter this open feed water heater and mix together. That's why it's called an open feed water heater, because the two inlet streams are allowed to mix. So they mix together and go out this exit here. So an open feed water heater has two inlets and one exit. And like I say, it could be as simple as just a T in the line. We have this pipe flowing along and then this is T'd into it. Schematically, I'll just be showing it as a box like all of our heat exchangers are. Now the other thing you'll notice about an open feed water heater is that our Rankine cycle now has two pumps. Well, two pumps are necessary because eventually we need to get from the condenser pressure all the way up to the steam generator, but we can't do that with a single pump because our open feed water heater has to operate at some intermediate pressure between the condenser pressure and the steam generator pressure. And that's just a matter of design, exactly what pressure we want that to be, and we'll be playing around with that a little bit later on. But for now, all we need to know is it's some pressure between the condenser and the steam generator pressure. So if this open feed water heater is going to operate at that intermediate pressure, it means we can't have a single pump taking us all the way up to the steam generator pressure. The first pump needs to take us from the condenser pressure to the open feed water heater pressure, allows these to mix, and then the second pump takes that mixture and pressurizes it the rest of the way up to the steam generator. So one thing about an open feed water heater is that it necessitates that we have two pumps. So as soon as you see one of these Rankine cycle open feed water heaters, you'll notice that 2 pumps are required, where before we only needed 1. Now on a TS diagram, everything is very similar to before, except we have this extra process. So notice the process through the 2 turbines, 1 to 2 and then 2 to 3 is over on the right side here, and these are still isentropic turbines, so these are still perfectly vertical lines. And notice there's no reheat, so we don't come down here and then reheat and come down like we did when there was a reheater. We're just extracting a portion of the steam at that point. So for every kilogram that goes through this turbine, perhaps only 0.9 kilograms will continue on through this turbine, and the rest will be extracted to go to the steam water heater. Exactly how much steam we extract here is a matter of design and also of operation. We might adjust that in order to adjust certain parameters for this cycle as it's operating. But in general, a relatively small fraction is extracted, and that's called the extraction fraction. So point 2 here is the properties, the temperature and entropy of the steam being extracted there. Now, if we look at the other side, point 4 is the exit of our condenser, so that's right there. It goes through the first pump, and it's an isentropic pump still, so it goes straight up. This point 5 is at the open feed water heater pressure, so this purple line is a line of constant pressure at the pressure of the open feed water heater. So that's where point 2 is. It's at that pressure, and point 5. So point 2 and point 5 mix together and come out at point 6. So point 2, so a small flow rate with these conditions and a large flow rate with those conditions get mixed together, and it comes out at point 6, which is right there. So that's the exit of our feed water heater, is right there. So a large flow of this combined with a small flow of that gives there. So you can see the effect of this open feed water heater is the heating process from here up to here has taken place using some energy we stole from inside the cycle. So it greatly reduces the amount of heat we need to add in the steam generator. The inlet to the steam generator is now way up at this higher temperature instead of being way down here. So the steam generator requires much less energy because of this open feed water heater being there. Now we're going to be doing examples later on where we'll be able to put some numbers to all of this and just see how much effect the open feed water heater has. The other style of feed water heater that we want to look at is a closed feed water heater. So again, over on the turbine side, I'm showing 2 stages of the turbine. There's no reheat here. I've just split it into 2 stages so we can have an extraction point. Over on the other side, we have our pump, and it goes, so this is the feed water coming out of the pump towards the steam generator, and it goes through this closed feed water heater and then to the steam generator. Notice there's no second pump here. So for a closed feed water heater, this pump takes us all the way from the condenser pressure all the way up to the steam generator pressure. And it can do that because of the nature of this heat exchanger. The meaning of closed feed water heater is that the feed water going through it and the extracted steam coming through it do not mix. There is a pressure boundary between those. So this would typically be a shell and tube heat exchanger. So because of that, this feed water and the extracted steam can be at very, very different pressures. So there's no need for a second pump then. We can let a single pump fully pressurize us up to the steam generator before we enter the closed feed water heater. So there is certainly heat transfer within this closed feed water heater. This is the hot side, the extracted steam going through it. This is the cold side, the relatively cool condensate coming from the condenser. So heat is transferred from the hot side to the cold side, but of course heat transfer with the surroundings would be relatively small. Now, because those two fluid streams do not mix in a closed feed water heater, a closed feed water heater will have a second exit. So the extracted steam comes in here, gives up a bunch of its energy to preheat the water going to the steam generator, and then comes out here. Remember, the open feed water heater had 2 inlets and 1 exit. closed feed water heater has 2 inlets and 2 exits. Now this extraction is still happening at some intermediate pressure between the condenser pressure and the steam generator pressure. So this pressure in this line is still higher than the condenser pressure. So what is done is that's trapped, or it goes through what is called a steam trap into the condenser. Now a steam trap we can just think of as a throttling valve. So this is just a pressure drop across this to get into the condenser. And so that steam, after it gives up a bunch of its energy to the feed water, is just dumped into the condenser so that it can continue on, rejoin the main loop here, and go through the steam generator and the first stage of the turbine again. So that's our layout of components, at least schematically, for a closed feed water heater. TS diagram, again we have our turbine stages here, which take us all the way from 1 down through 2 to 3. So point 2 is our extraction point. So that's the properties of the steam that is extracted and fed to the closed feed water heater. We have just a single pump now, so we go all the way from our condenser pressure all the way up to our steam generator pressure with a single pump process, 4 to 5. What the closed feed water heater is doing is taking the flow at 5, that's one of its inlets, the flow at 2, which is a much lower flow rate but a much higher temperature. Heat is transferring from this flow at 2, so it cools off, and I've shown it going all the way to here, so it's almost a saturated liquid under these particular operating conditions. And then it's trapped down to point 8. So this is the throttling process through this so-called steam trap here. Well, all of the energy that this feed water gives up as it goes from here to here serves to increase the temperature of the feed water from here to here. So point 7, which is right there, is our new inlet into the steam generator. So because this feed water heater is installed and operating, we save this amount of heat from being added in the steam generator. We move the inlet of the steam generator from this point up to this point. So less heat is required from whatever external source we happen to be using. So this is just contrasting the two, just showing them side by side to show the differences. So key differences are, with an open feed water heater we need 2 pumps because this open feed water heater is just an open chamber that needs to operate at this intermediate pressure. Closed feed water heater, we just have a single pump because this pump can take us all the way up to the steam generator pressure right away, because this stream and this one do not need to be at the same pressure because they do not mix. There's a pressure boundary between them, likely in the form of a shell and tube heat exchanger. Other differences here is when the extracted steam is finished in the closed feed water heater, it comes out, goes through a trap into the condenser, and of course here it is mixed with the feed water, so there's no second exit. Both the feed water and the extracted steam both exit as a mixture into the second pump. So those are the big differences in the layout between an open feed water heater and a closed feed water heater. But realize they're both achieving the same thing. They're both stealing some energy from a high temperature portion of the cycle, that is partway through the turbine expansion, and using it to preheat the water before it goes into the steam generator. So this is just a picture of an advanced or more advanced Rankine cycle that brings all of these things in play at the same time. So we'll just go through this. So we have our steam generator, which would be producing superheated steam here, going through a first turbine stage and then through a reheater. So this is combining both reheat and open and closed feed water heaters. Second turbine stage is receiving steam from the reheater, and there's some extraction here which we see is going to a closed feed water heater. Then our third turbine stage, and then some more extraction which we see is going to an open feed water heater. So it's very typical in these systems to have multiple extraction points along the turbine. So conceptually here at least, we divide the turbine up into multiple stages to show clearly how that happens. So after this second extraction, we go through a fourth turbine stage, and then there's a second reheater, and then finally to our fifth turbine stage. And then from the fifth turbine into the condenser, as we always have. So if we go back here and look at our closed feed water heater, it's operating at a higher pressure than the open feed water heater because its extraction is closer to the steam generator at a higher turbine stage. So the extracted steam comes out of there. Then it goes through a trap to drop its pressure down. But notice instead of going into the condenser, it's quite typical to pass this into the open feed water heater. And it turns out actually that helps the efficiency. So if we were to trap this directly into the condenser as opposed to putting it into the open feed water heater, this particular configuration is better because it has an overall higher plant efficiency. And we'll see that when we start playing with some calculations here in a few moments. So notice now this open feed water heater actually has three inlets. The main feed water coming from the pump, its own extraction point, and also the extracted spent steam from the closed feed water heater is dumped in there as well. So 1, 2, 3 inlets, but still only a second outlet. Now notice this layout needs two pumps because it has an open feed water heater. So the first performance parameter that we've talked about quite a bit is the thermal efficiency, and that's the net work divided by the heat supplied. Here they're both expressed as rates, and that's typically how we would be viewing them. Another performance parameter, though, used for all power cycles is something called the back work ratio. So the back work ratio, or BWR, is the magnitude of the pump work divided by the turbine work. And again, it's a positive number, that's why we take magnitudes. So this is essentially saying that for all of the work that the turbine produces, how much of that is required to go back into the cycle to run the pump. So pump power divided by turbine power is the back work ratio. And as we'll see when we do some calculations later on, for a Rankine cycle, the back work ratio is really quite small. That's one of the positive features of a Rankine cycle, is that of all of the power it produces in the turbine, only a very small fraction of it is required in the cycle itself to keep it running. So very, very small back work ratio, typically about 1%, but we'll do some calculations of that later on. The next thing I want to look at is the effect of turbine efficiency. All of the TS diagrams that we've looked at so far have had 100% efficient turbines. And here's just an illustration we've seen before. So this Rankine cycle has a single reheater. We can see the reheat process there. And both of the turbine stages are 100% efficient because they're vertical lines on the TS diagram. Well, if we adjust the isentropic efficiency of a turbine down to 80%, then it's going to look like this. And realize that these plots are drawn to scale, so this is actual data that's being used. So as we go through the first turbine stage, we drift off to the right, so we'll hit this reheater pressure at a higher temperature. And as we go through the second turbine stage, we'll also drift off to the right. So notice one of the effects of inefficient turbines is actually to reduce and perhaps possibly remove liquid from showing up at the low pressure end of the turbine. Here we have a little bit of liquid showing up at the low pressure end of the turbine, but if the turbine efficiency is reduced, we'll see that actually the exit of the turbine is now a superheated vapor. So the very first parts of the condenser actually is just cooling off the water vapor. It doesn't start to condense right away until it gets to that point there. Now, certainly we still want to have our turbines as efficient as possible. That's going to contribute positively to the overall plant efficiency. But one benefit of the turbines being a little bit inefficient is that they are more likely to operate out in the superheated region like this. So that's the effect of turbine efficiency. The next thing I want to illustrate here is the important effect of the condenser pressure. So I've just shown two cases here with two possible values for the condenser pressure. This one is 10 kPa and this one is 100 kPa. So this one is essentially atmospheric pressure, and this one is down much lower than atmosphere, about 1/10 of an atmosphere. Now it turns out that operating Rankine cycles much prefer to have condenser pressures that are very low. In fact, they might even be lower than this 10 kPa. And in fact, it turns out we want them to be as low as possible, and we'll show why here. If we look at the efficiency of this cycle on the left, so this is the thermal efficiency of the entire cycle, for all of the other operating parameters that I've got here, it turns out to be 40.36%. If the only change we make to this cycle is increasing the condenser pressure up to 100 kPa, all other things are kept constant. If we redo this calculation, we'll find that the thermal efficiency drops way down to 33.19%. So this is a very, very bad thermal efficiency compared to this one. So the bigger difference we can get between the steam generator pressure and the condenser pressure, the higher our thermal efficiency will be. We want that to be as low as possible, and we want that to be as high as possible. So condenser pressures in operating Rankine cycles are as low as we can possibly get them, so that we get this temperature down here at which heat is being rejected as low as possible. Notice this temperature is down around 50 degrees, perhaps a little bit less, whereas this temperature is up at 100 degrees. So we want that temperature that we're rejecting heat to be as low as possible. Likewise, haven't illustrated it here, but we would like this temperature that we're adding heat at to be as high as possible. And this actually goes back to our expression for the thermal efficiency of a Carnot cycle. So even though this is not a Carnot cycle, the expression for the Carnot efficiency still tells us the two main parameters that we can change to increase our efficiency. We want that to be as small as we possibly can, and we want that to be as high as we possibly can make it. So this is a goal, a design goal in every power cycle, is to make TC as cool as we can and to make TH as hot as we can. Well, in terms of the condenser in a Rankine cycle, having the condenser pressure low is the same as having the cool temperature TC low. So why are these changes in thermal efficiency important? Well, let's take a look at a 1 gigawatt electric power plant. So that's what this notation means. It produces 1 gigawatt of electrical power. So this is the final output of the power plant. Well, let's say that you do something and you manage to turn a valve or adjust a knob somewhere in the control room, and you're able to increase the thermal efficiency of that cycle from 45 to 46%. Now that might seem like a very, very small change that's not really worth doing, but it is most absolutely is worth doing. So this is a scenario we want to look at. A 1 gigawatt electric plant, which is a fairly large plant but not unreasonable, and an increase in the thermal efficiency from 45 to 46%. Well, let's first of all look at this environmentally. So we're going to produce 1 gigawatt electric no matter what. So as this increase in thermal efficiency is affected, as you do something to increase that thermal efficiency, if you maintain the same plant output, that means you're going to be able to use a little bit less fuel, whatever that happens to be. So for a 1 gigawatt plant, increasing the thermal efficiency from 45 to 46% reduces the heat input required by about 1.5 times 10 to the 12 kilojoules per year. Now it's kind of hard to have a feel for that, but that is a lot of energy. Now if we assume that this thermal power plant is fueled by methane, which is fairly typical these days, so if we have methane fuel, then the greenhouse gases attached to that is about 77 million kilograms of CO2 per year. So a very, very small change in thermal efficiency, a very significant reduction in the greenhouse gas emissions. So 77 million kilograms of CO2 less emitted into the atmosphere with that increase in efficiency. So this is why large thermal power plants are doing everything they can to increase that efficiency. Small efficiency gains make a very big difference to the greenhouse gas emissions that they're producing. Now another way to look at this is economically. So let's say that we just keep the heat input the same. So we're burning the same amount of fuel, whatever that happens to be. So QH is constant, but this increase in efficiency allows us to increase the output of the plant, and assuming that we can sell that, of course. So if we sell electricity for 15 cents per kilowatt hour, which is sort of a generic typical number in Canada, then this increase in efficiency would increase the revenue of this 1 gigawatt plant by about $13 million per year. So a very significant increase in the revenue based on a very, very small increase in the thermal efficiency. So this again is why these thermal power plants are constantly striving to increase the efficiency, both in the original design of the plant and also in its operation.